Hey guys, today we're going to look at the connections between a function, its first derivative, and the second derivative. So first, let's review the connections between the first derivative and what that tells us about the function. So we're going to fill out this chart here. If f prime of x is greater than 0, then that means that f of x, my function, is going to be increasing. If f prime of x is less than 0, then that means the function is decreasing. And again, this should all be review, but just in case, it's always good to review. If f prime of x is equal to 0 or is undefined at some value of x, so x is equal to a, then that means two things. One, there is a critical number at x is equal to a, and two, there is a possible extrema, so either a minimum or a maximum. If the first derivative changes from positive to negative, then that means that there is a maximum in the function. If the first derivative changes from negative to positive, then that means there is a minimum in the function. So let's practice review how to get all this information based on the function. Here we have f of x is equal to x to the fourth minus 4x to the third. So first we need to find the derivative so that we can determine those critical numbers. So f prime of x is going to equal to 4x to the third minus 12x squared. We're going to make this equal to 0 because our critical numbers are when the first derivative is equal to 0. And then we're going to factor so that we can find those values of x. 4x to the third minus 12x squared, we can factor out a 4x squared. And then that would give me x minus 3. If I solve individually, our critical numbers are going to be x is equal to 0 for the 4x squared and x is equal to 3. Now we're going to create our number line with those critical numbers. I'm going to plug in a number to the left of 0 into my f prime of x. So let's say I plug in negative 1. 4 times negative 1 squared, which will become positive 1. This is a positive. And negative 1 minus 3 is a negative. So a positive times a negative would give us a negative number. If I plug in a number between 0 and 3, let's say 1, this would be positive, and then 1 minus 3 would also be negative. And finally, if I plug in a number to the right of 3, so let's say 4, this factor here would be positive, and this would be positive, so my answer would be positive. Now this is important. On the number line, I like to label it simply because we are going to be using number lines for both the first and second derivative, so it's good for the AP reader to know what number line represents. But your number line here is good to organize information about your function, but it's not enough to justify any answers. So that's why we've been practicing putting things into sentences, because this is what's actually graded. So for f of x is increasing, we have to look at when the first derivative is positive. And the first derivative is positive in this section here. So it would be increasing on the interval 3 to infinity. And we would say because f prime of x is greater than 0. Now f of x is decreasing on these two intervals. Remember that 0 is a critical number, meaning that the derivative is equal to 0, which is not negative. So if it's separated by a critical number, we will have to stop at that number. So f of x is decreasing on the interval negative infinity to 0, union 0 to infinity, and we would say because f prime of x is less than 0. Now f of x has or does not have, that's what we're going to determine now, a relative maximum. Now over here, remember, a maximum occurs when the first derivative changes from positive to negative, which it never does. So it does not have a maximum. We won't need to write anything here, and we would say because f prime of x does not change from positive to negative. And finally, f of x has or does not have a relative minimum. A minimum occurs when it changes from negative to positive, which is right here at x is equal to 3. So it does have a relative minimum at x is equal to 3, and we would say because f prime of x changes from negative to positive. So this is just a review of the first derivative and what that tells us of the function. But let's take a closer look at critical numbers. Now, critical numbers occur when the first derivative is equal to 0, and that we know. And we have talked about places where a function is not differentiable, such as a cusp, but that does not exclude the existence of a relative maximum or minimum. So it's important to note that critical numbers of a function not only occur when the derivative is equal to 0, but also when the derivative is undefined. So even though we may have a cusp at a particular x value, it could still be considered a critical number because it could be a maximum or a minimum, regardless of whether it is a cusp or not. So as an example, we're going to look at this function. F of x is equal to x plus 2 raised to the 2/3 plus 1. Now I have the graph here so you can see what I'm talking about. So we're going to find the first derivative, and we're going to determine intervals of increasing and decreasing behavior, as well as the maximum or minimum. Now, obviously, I know what the answers are going to be because we have the graph. And if you had the graph, you didn't have to go through all of this because you would use the graph. But we're going to do this by hand and then confirm our analysis with the graph. So let's first find the derivative, f prime of x. Now, this is going to be the chain rule because of this exponent. So we're going to bring the exponent to the front, subtract 1 from the exponent, which would be negative 1/3, and then derivative of 1 is 0. So this is my derivative, because the derivative of the inside that I would have to multiply is just 1 anyway. So let's rewrite this a little nicer. Because of this negative exponent, that means it's going to go down to the denominator. So 2 over 3, and then that is a cube root of x plus 2. So this is my derivative. Now, as you can see, at x is equal to negative 2, my denominator would equal to 0, meaning that the function, or the derivative of the function, is not, okay, sorry, let me rephrase. That is not differentiable at x is equal to negative 2 because it is undefined. However, that is still our critical number. So I'm going to still create my number line using negative 2. And now I'm going to plug in some numbers. So let's say I plug in negative 3. If I plug in negative 3 into the denominator, we get 3 times the cube root of negative 1, because negative 3 plus 2 is negative 1. And the cube root of negative 1 is negative 1. So that means that we would have a positive divided by a negative, which is a negative number. And if I plug in a number to the right of negative 2, so let's say negative 1, down here we would have negative 1 plus 2, which is a positive number. So everything would be positive, making this positive. Now, let's determine all of our intervals of increasing and decreasing behavior. So we would say that f of x is decreasing on the interval negative infinity to negative 2 because f prime of x is less than 0. Then we would also say that f of x is increasing at x is, got ahead of myself. I was thinking about the extrema. Okay, so f of x is increasing on the interval negative 2 to infinity because f prime of x is greater than 0. Now, as you can see, in order to determine maximums or minimums, we can see that the only kinds of extrema we have here is a minimum. So we can say f of x has a minimum at x is equal to -2 because f prime of x changes from negative to positive. And then we would also say that f of x does not have a maximum because f prime of x never changes from positive to negative. And if you look at your graph here, from -infinity to -2, my graph is indeed decreasing. And then from -2 to infinity, my graph is increasing. And here is the minimum value. So everything that we found here is confirmed on the graph. So again, this is just to emphasize the fact that our critical numbers even occur not only when the derivative is 0, but also when the derivative is undefined. Now let's look at the second derivative. Now the second derivative tells us information about both the function and the first derivative. If the second derivative is greater than 0, what this tells us is concavity. So this is the difference. This means concave up. So it kind of looks like a cup. So that's how I remember concave up, cup. And if it's concave down, it looks like this. So that is the difference between concavity, concave up, and concave down. So if f double prime of x, so if the second derivative is greater than 0, that means that the function f of x is concave up. Now, what does the second derivative tell us about the first derivative? The relationship between the second derivative and the first derivative is the same as the first derivative to the function. So if the second derivative is greater than 0, that means that the first derivative is increasing. So just like how if the first derivative is greater than 0 and then the function is increasing, it's the same exact relationship as the second derivative with the first. So let's try when the second derivative is less than 0. When the second derivative is less than 0, then that means that the function is concave down, which also means that the first derivative would be decreasing. When f double prime of x is equal to 0, that would be a critical number for the second derivative, or if it's undefined. And what that tells us is that we have a point of inflection. Now, a point of inflection means that it changes concavity. So for example, I'm going to draw a little picture here. You see how here, this is concave down up until right about there. And then here it's concave up. That point here, that's the point of inflection. Now, if your second derivative is equal to 0 or undefined, that means that the first derivative has a possible extrema. So either a minimum or maximum. So again, just like when the first derivative is equal to 0 or undefined, there is a possible minimum or maximum for the function. It's the same thing. For the second derivative, if it equals to 0, then that means that for the first derivative, there is a possible extrema. When the when the second derivative changes from positive to negative. Okay, so for the second derivative, this is a little bit different. When the second derivative just changes signs, so either it changes from positive to negative or changes from negative to positive, this means that there is a definite point of inflection. So sorry, let me rephrase this here. When it equals to 0, there is a possible point of inflection. It could be a point of inflection or it may be something else going on, but when it changes signs, that means it's definitely changing concavity, so either changing from concave up to down or concave down to up. There is a definite point of inflection for when the second derivative changes signs. And then if the second derivative changes from positive to negative, then that means that the first derivative has a maximum. And if it changes from negative to positive, that means that the first derivative has a minimum. Now let's continue working with that function we had found before, right? The x plus 2 raised to the 2/3 plus 1. And we had found that the first derivative is equal to 2 over 3 x plus 2 raised to the 1/3, or the cube root of x plus 2. Now I'm going to rewrite this as 2/3 x plus 2 to the negative 1/3, just because I'm going to find the second derivative now. In order to find the second derivative, it's just finding the derivative of the first derivative. So it just creates like a chain. So here we go. F double prime of x is the derivative of the first derivative. So I am going to apply the chain rule once more. So we're going to multiply this negative 1/3 to the 2/3, which gives us negative 2 over 9 times x plus 2 raised to the negative 4 over 3, because I subtracted 3 over 3 from the exponent. And then the derivative of x plus 2 is just 1. So this is my second derivative, which I can rewrite as negative 2 over 9 to the cube, and then 9 cube root of x plus 2 to the 4th. So now we're going to find our critical numbers. And as you can see, in the denominator is where we have the x plus 2. So our critical numbers are x is equal to negative 2. So it's the exact same critical number as before. So we're going to create our number line now. So f double prime of x, this is why I label my number lines, because now we have a number line for both f prime and f double prime. Like if this was one problem, you would need to be able to organize your work. So let's plug in a number to the left of negative 2. So let's say negative 3. And if you put negative 3 in the denominator, it would be negative 3 plus 2, which is negative 1, but it's being raised to the 4th. And negative 1 raised to any negative number raised to an even exponent would make it positive. So this would be a negative divided by a positive, so negative. And if I were to plug in a number to the right of negative 2, so let's just say negative 1, same situation. It would be negative 1 plus 2, so it would be positive. So a negative divided by a positive is also a negative. So we can see here, because the second derivative is only negative, to answer this question, when is the function concave up, we would say f of x is never concave up, because f double prime of x is never greater than 0. Now concave down, the function is only concave down. So we would say f of x is concave down from negative infinity to negative 2 union negative 2 to infinity, because f double prime of x is less than 0. Now, where is there a point of inflection? There is only a point of inflection if the second derivative changes signs, which it doesn't. So we would say there is no point of inflection because f double prime of x never changes signs. And again, I have the graph here so you can see exactly what we were talking about. Here is negative 2. And as you can see, both sides of negative 2, the graph is concave down. But because this is undifferentiable, it is a cusp, and that therefore there is no point of inflection because it did not change concavity. Now let's look at putting all of this together. Here we have a function, and again, I'm giving you the graph just so that you can confirm all of your analysis from the graph. But we're going to do all of this by hand as if we didn't have the graph. So it says here to determine the open intervals for which the function below is increasing, decreasing, concave up, and concave down. And then we're going to find the coordinates of the relative extrema and any points of inflection, and then we're going to justify all of the reasoning. So in order to determine increasing, decreasing, we're going to find the first derivative. So f prime of x is equal to 3x squared minus 12x plus 9. We can factor out a 3, leaving us with x squared minus 4x plus 3. And remember, we want this to equal to 0. We're going to continue factoring. So 3, and then we have x minus 3, x minus 1 equals to 0. And therefore, my critical numbers are x is equal to 3 and 1. So now I'm going to go ahead and create my number line using these critical numbers, which are 1 and 3. And now I'm going to plug in numbers to test each interval into my derivative here. I like to use a factored version because it makes my analysis a lot easier. A number to the left of 1 would be 0. So if I plug in 0, this would be negative times a negative, so positive. If I plug in 2, this would be a negative times a positive, so negative. And if I plug in 4, everything would be positive, so positive. So now we would say f of x is increasing on the interval negative infinity to 1 union 3 to infinity because f prime of x is greater than 0. Now we can also say that f of x is decreasing on the interval 1 to 3 because f prime of x is less than 0. Now to figure out the minimum and maximums, okay, here we have a maximum at x is equal to 1, and here we have a minimum at x is equal to 3. Now, it does ask for the coordinates, so we have to take those values and we plug it into the original equation in order to get the y value. So just to save on some work, we can use the graph for this. If I plug in x is equal to 1, my y value is 5. And I mean, you can test it out, right? So 1 to the third is 1 minus 6 times 1 squared, so 6 plus 9 plus 1, which would equal to 1 minus 6 is negative 5. Negative 5 plus 9 is 4, and 4 plus 1 is 5. So we have here f of x has a maximum at 1, 5 because f prime of x changes from positive to negative. Now, f of x has a minimum at, now we know the minimum is going to be at x is equal to 3. And again, just to save on some time, at x is equal to 3, the y value is 1, so we could say f of x has a minimum at 3, 1, because f prime of x changes from negative to positive. Now, to figure out everything else, right, the concavity, concave up and concave down, that means we need the second derivative. So here is my first derivative. It's easiest to find the derivative of a polynomial type function, so I'm going to use this one here. So the second derivative, let's actually do this in a separate color so we can kind of organize our work here. Okay, so the second derivative, f double prime of x, is going to equal to 6x minus 12. And we make that equal to 0 to find our critical numbers. We can factor out a 6, and that would give us x minus 2 is equal to 0. So my critical number here is x is equal to 2. And so now I'm going to create my number line, f double prime of x, with my critical number of 2. I'm going to plug in a number to the left of 2, so 0. 0 minus 2 is negative, so negative. And if I plug in 3, then I get positive. So now this tells us my concavity. We would say f of x is concave down on the interval negative infinity to 2 because f double prime of x is less than 0. And then we would say f of x is concave up at or on the interval 2 to infinity because f double prime of x is greater than 0. Now to find the point of inflection, since the second derivative changes signs, there is a point of inflection at x is equal to 2, but we need the y value. So we can take the 2 and plug it in, or we can look at the graph since I have the graph right now. At x is equal to 2, the y value is 3. So we would say that f of x has a point of inflection at 2, 3 because f double prime of x changes signs. So as long as it changes signs, we have a point of inflection. So you don't have to say that it changes from positive to negative or negative to positive. Now normally I don't like to do a lot of slides in one lesson, but it's important that we understand all of these connections. And so we're going to be doing a lot of writing today. Now we're going to focus more on analyzing these graphs and getting all of the information that we can get from the graphs. As you can see with f of x, this is a lot of information that we get about the first derivative and the second derivative. So let's go ahead and start with the first derivative. So sometimes, like I have here sentence frames that we can fill out. It is up to you on how you state your information. You don't have to write it exactly how I do. As long as you have all of the information that is needed, you're good to go. So what I do a lot of the time is I first figure out the reasoning that I would need in order to justify when f prime of x is greater than 0, and then I would look for that on the graph. So for example, I know that the function when f prime of x is greater than 0 would be increasing. So I would write here because f of x is increasing. So now I'm going to look on the graph where my function is increasing. Now we can see it is increasing from here to here and then from here to here. So we would say on the interval negative infinity to negative 5 union negative 2 to 1. And again, because f of x is increasing. Now, when f prime of x is less than 0, that means that the function is decreasing. So I'm going to look here when my graph is decreasing. So we can see that it's from negative 5 to negative 2, union from 1 to infinity, and because f of x is decreasing. Now, when is f prime of x is equal to 0? And f prime of x is equal to 0 at any extrema, so at these points. So f prime of x is equal to 0 at x is equal to negative 5, negative 2, and 1, and we would say because f of x has extrema. Next, we have f prime of x changes from negative to positive. So that means that we're looking for on the graph when the function has a minimum. And the function has a minimum here at x is equal to 2, negative 2. And again, we would say because f of x has a minimum. F prime of x changes from positive to negative. That occurs when f of x has a maximum. So we have these two values at x is equal to negative 5 and 1. because f of x has a maximum. Next we have f prime of x is increasing. So when is the first derivative going to be increasing? Now the only way that I know when f prime of x is increasing is when the second derivative is changing signs. So, when the second derivative is positive, meaning that the function is going to be concave up. So now we have to look for, or have to switch gears and look for when the function changes concavity. So here this is concave down to right about here. Then it's concave up to about, I would say, right here. So it's usually like right in between of the 2 points for the concavity. And then it's concave down again. So we would say f prime of x is increasing, and this is the only section where it is concave up. So this is about negative 3.5 to about negative 0.5. Now, when you're writing your reasoning for these, for any of this, if you're given the graph, has to be in terms of the graph. I know that it's increasing because the second derivative is greater than 0, but that's not the graph that's given. The graph that's given is f of x. So we would say because f of x is concave up. Now, f prime of x is decreasing when the second derivative is negative, meaning that we're looking for when the graph is concave down. So this is concave down here. So we would say from negative infinity to negative 3.5 union, because it's concave down again, from negative 0.5 to infinity. And again, we have to justify using the function. So we would say f of x is concave down. Now, f prime of x has a relative maximum. Now, the first derivative will have a maximum when the when the second derivative changes from positive to negative, meaning changing from concave up to concave down. And when it changes from concave up to concave down is right here at negative 0.5. So x is equal to negative 0.5, and we would say because f of x changes from concave up to concave down. And same thing here, f prime of x has a relative minimum, and this occurs when it changes from concave down to concave up, which only occurs here at x is equal to negative 3.5. And the reasoning would be because f of x changes from concave down to concave up. Now looking at the second derivative, f double prime of x is greater than 0. Now it is greater than 0 when it is concave up. So these are going to be the exact same answers as when f prime of x is increasing or decreasing. So f double prime of x is greater than 0 on the interval negative 3.5 to negative 0.5. And we would say because f of x is concave up. So again, it is like almost the exact same, it is the exact same statement as these two right here, because f prime of x is increasing when f double prime of x is greater than 0. So now this is the same reasoning. F double prime of x is less than 0, and this is when my function is going to be concave down. So it's the exact same statement as we have written here, because that also occurs when f prime of x is decreasing. So we would say on the interval negative infinity to negative 3.5 union negative 0.5 to infinity, and we would say because f of x is concave down. And I just realized here that I put down here. This would be up. My bad. And finally, f double prime of x is equal to 0, and that is when it changes concavity, and it changes concavity at those 2 points. Those are those points of inflection. So we would say at x is equal to negative 3.5 and negative 0.5, and we would say the reasoning for that would be because f of x has points of inflection. So this is a lot of information that the function tells us. So the function not only gives us information about the first derivative, but it also gives us a lot of information about the second derivative. All right, now let's have a look at the first derivative and see what kind of conclusions we can make about the second derivative and the function. So the graph here that's given, like I said, is the first derivative. So that means that all of our justifications have to come from the behavior of the graph of this first derivative. As I mentioned before, sometimes it's helpful to think of the reasoning before you look at the graph, so that way you know what it is that you're trying to look for when you look at the graph. So for example, let's start here with the function. F of x has a relative minimum. Now remember that this is the graph of f prime, and f of x is going to have a minimum when the derivative changes from negative to positive. So we're looking for these x-intercepts. So here this is negative and this is positive, and then here is negative and here is positive. So f of x has a relative minimum at x is equal to negative 3 and 3, and because, and we would remember we have to use the first derivative for my reasoning, because f prime of x changes from negative to positive. Now f of x is going to have a relative maximum when f prime changes from positive to negative, which occurs at x is equal to 1, and we would say because f prime changes from positive to negative. Now f of x is increasing. F of x is increasing when the derivative is positive. So this is going to be from negative 3 to 1, because everything above the x-axis is positive and everything below the x-axis is negative. So from negative 3 to 1, and then again from 3 to infinity. And we would say because f prime of x is greater than 0. And f of x is decreasing when the derivative is negative. So that's here and here. So we would say from negative infinity to negative 3, union from 1 to 3, because f prime of x is less than 0. Now, f of x is concave up when the second derivative is positive, which also occurs when the first derivative is increasing. So that's what we need to look for on this graph, when my first derivative is increasing. So it's increasing here up until this point, and then decreases until here, and then increasing again. So f of x would be concave up from negative infinity until negative 1, union from 2 to infinity. And we would say because f prime of x is increasing. Now f of x is concave down. So I keep repeating myself, and it's just so that you can really see this connection. F of x is concave down when the second derivative is negative. And the second derivative is negative based on the first derivative if it's decreasing. So remember that the relationship between the first derivative and the second derivative is the same as the relationship between the function and the first derivative. So if the first derivative is increasing, the second derivative is positive. And if the first derivative is negative, the second derivative, if the first derivative is decreasing, then the second derivative is negative. So that's what we need when the first derivative is negative. decreasing. Oh my gosh, I'm so sorry. So decreasing, which is from -1 to 2. And we would say because f prime of x is decreasing. Now, when is f double prime of x greater than 0? And this is going to be the same statements basically as these, because f double prime of x is greater than 0 means that f of x is concave up. So these are essentially the same thing. So we would say on the interval from -infinity to -1 union 2 to infinity, because f prime of x is increasing. And again, you see the relationship here between the second derivative and the first. When the second is greater than 0, the first is increasing. And when the second derivative is less than 0, the first derivative is going to be decreasing. So now it's decreasing from -1 to 2. And f double prime of x is going to equal to 0. So remember, the second derivative will equal to 0 when the first derivative has any kind of extrema, which occurs here and here. So this is at x is equal to -1 and 2 because f prime of x has extrema. Now let's examine the graph of the second derivative. Okay, so like I said, here we have the graph of the second derivative, and we're going to get all of this information about the first derivative. So f prime of x has a relative minimum. Now you can kind of pretend like as if we're looking here at the first derivative and writing information about the function, because the relationship, as I keep saying, is the same. So the first derivative will have a relative minimum at x is equal to 0. And this is because f double prime of x changes from negative to positive. Now, f prime of x is not going to have a relative maximum, and this is because the second derivative here, as you can see, does not change from positive to negative. It's positive all here, but it doesn't come back and become negative. So we would say does not have a relative maximum because f double prime of x does not change from positive to negative. Now, f prime of x is increasing. So f prime of x would be increasing when the second derivative here is positive. So that would occur from 0 to 3 union 3 to infinity. Remember that you always have to stop at any x-intercepts, because there the derivative is 0, not positive. And we would say because f double prime of x is greater than 0. F prime of x is decreasing, and it's decreasing when it's negative, which is down here. So we would say from -infinity to 0 because f double prime of x is less than 0. F prime of x is concave up. Now this one's a little bit tricky to understand, but f prime of x is going to be concave up when f prime of x is increasing. So the relationships are the same between the derivative and the first, and then the first to the second, and then it's the same thing from the function to the second derivative is the same as the first derivative to the third derivative. So it's kind of like a loop-de-loop, and I'm sorry about that. But to kind of reiterate, f prime of x is concave up. So think about if we're talking about the function is concave up when the second derivative is positive. But in this case, we're looking at the first derivative, so then that would mean that the third derivative would have to be positive. And that would occur when f double prime of x is increasing. So we would say f prime of x is concave up from -infinity to 1 union from 3 to infinity. And the reason would be because f double prime of x is increasing. Similarly, for concave down, it's when the function is decreasing, or when the second derivative is decreasing, which occurs from 1 to 3. And again, we would say because f double prime of x is decreasing. Now for the function, f of x has a point of inflection at. Now, f of x will have a point of inflection when the second derivative is changing from positive to negative or negative to positive, which only occurs here at x is equal to 0. So we would say f of x has a point of inflection at x is equal to 0 because f double prime of x changes signs. F of x is concave down when the second derivative here is less than 0. So right here, so that would be from negative infinity to 0, and this is because f double prime of x is less than 0. And finally, for concave up, it is when the function, the second derivative is above the x-axis. So from 0 to 3, union 3 to infinity, and again we would say because f double prime of x is greater than 0. Next, we're going to look at something called the second derivative test. Now, what the second derivative test is used for is to determine the intervals of concavity and points of inflection. That's what the second derivative is used for. But it can also be used as an alternative way of identifying any relative extrema. And this is how. If we know that x is equal to a is a critical number of f of x, then that means that f prime of a is equal to 0 or it's undefined, making that value of x at x is equal to a, whatever that is, a potential maximum or minimum. Now, if we get that critical number and we plug it into the second derivative, and if that second derivative at that x value is greater than 0, that means that f of x is concave up at x is equal to a. And if it is concave up, this is what it would look like. That means that we would have a minimum. If you plug in that value of x is equal to a and into the second derivative and it's negative, less than 0, then that means that it is concave down, meaning that we would have a maximum. And finally, if you plug it in and you get that the second derivative is equal to 0 at that x value, then we can't say there is no relative, it's not a relative maximum or minimum. So here's an example of exactly what I'm talking about. This is the graph of f of x. And f of x has a relative maximum at x is equal to -2, which we can see here. And this is because f prime of -2 is equal to 0, right? You can see that we have that horizontal tangent there. And we also see that it is concave down, meaning that the second derivative is less than 0. So that's just kind of like proof of the second derivative test. And it's the same thing here. If f of x has a relative minimum at x is equal to 1, which you can see right there, that's because we have a horizontal tangent, so that means that the first derivative is equal to 0 at x is equal to 1. And also, since it's concave up, that means that the second derivative was positive. So now let's test that out. Okay, here we have f of x is equal to x to the 4th minus 4x to the 3rd plus 2. And we want to use the second derivative test to find the relative extrema of the function. So in order to use the second derivative test, I put some steps here. We're first going to find the critical numbers of the function by setting the first derivative equal to 0. So let's find f prime of x, which is equal to 4x to the 3rd minus 12x squared, which can be factored. I can factor out a 4 and an x squared, which leaves us with x minus 3. And we're going to make this equal to 0. So now my critical numbers are going to be x is equal to 0 and 3. And now instead of doing my line chart and all that stuff, it's just another way of doing the same thing. But sometimes in the AP exam, they're very specific. Use the second derivative test or prove that something is a maximum or minimum based on the second derivative test. So what we're going to do now is we're going to take these two x values and we're going to plug it into the second derivative. So first, I need to find the second derivative. Here is my first. So my second derivative would be 12x squared minus 24x, which I can factor, so that way it's just a little bit easier when I plug in numbers. I can factor out a 12x, and I would have x minus 2. Now I'm going to go ahead and plug in x is equal to 0 and x is equal to 3. So when x is equal to 0, I don't know why I wrote it like that. Let me erase that. Give me 1 second. Okay, so first I'm going to write f double prime of 0. And when I plug it in, I get 0 times negative 2, which is just 0. And now I'm going to find f double prime of 3. And when I plug that in, I get here 36 times 3 minus 2, which is just 1, so 36. So now this at f double prime of 0, since it equals to 0, this is not any kind of extrema. It has to be either positive or negative. But since f double prime of 3 is equal to 36, that means that it is concave up at x is equal to 3. And at x is equal to 3, that means that I would have a minimum. So we would say that at x is equal to 3, f of x has a relative minimum because f prime of 3 is equal to 0 and f double prime of 3 is greater than 0. And that's basically it. You don't have to really say much more than that. You would have to state that the first derivative is 0 and that the second derivative is either positive or negative. Now let's look at this other example to apply this second derivative test. We have f of theta is equal to 2 cosine theta minus theta, and we want to find any critical numbers and any extrema on the interval 0 to 2 pi. So here we go. First, we need the first derivative. So f prime of theta, which is negative 2 sine theta minus 1. And to find their critical numbers, we have to make this equal to 0. And now we're going to solve for theta. And we're going to do that by first isolating the trig function. So I'm going to add the 1 and then divide the negative 2. So which would give me the equation sine theta is equal to negative 1 over 2. Because I'd add the 1, divide by negative 2, negative 1 over 2. And now we have to figure out, okay, what value of theta would give me a sine of negative 1/2. And this is based on your unit circle. So now our critical numbers are when theta is equal to 7 pi over 6 and 11 pi over 6. And as a reminder, I figured that out because I already know that the sine of pi over 6 is 1/2, but it's negative 1/2. And on the unit circle, sine is only negative in quadrants 3 and 4, and 7 pi over 6 and 11 pi over 6 are in quadrants 3 and 4. So I have my two critical numbers, and I'm going to hold on to that information. Now we're going to find the second derivative. So f double prime of theta is going to equal to negative 2 cosine theta, because it's this derivative right here. And now we're going to plug in these values. So f double prime of 7 pi over 6 is going to equal to negative 2 cosine of 7 pi over 6. Now, I don't necessarily need to know the actual value. I mean, it does help, but as long as you know where these angles are, 7 pi over 6 is in quadrant 3. And in quadrant 3, cosine is negative. So this would mean that I would have a negative times a negative number, which gives me a positive number. I don't know if that helps, or you can just, if you have those values memorized, you would just do negative 2, and the cosine of 7 pi over 6 is going to be negative square root of 3 over 2, which the 2's would cancel, and so would the negatives, giving me a positive square root of 3. But if you know that 7 pi over 6 is in quadrant 3, we already know that this value here is negative. And that's why I just did negative times a negative. I know it's positive. Now, if I plug in 11 pi over 6, 11 pi over 6 is in quadrant 4. And in quadrant 4, cosine is positive. So that means that I would have a negative number times a positive number, which gives me a negative. So again, not sure if that's helpful for you, or you can just plug in the value directly. This is negative 2 times the square root of 3 over 2. Again, the 2's cancel, and I'm left with negative square root of 3. So that is a negative number. So what does this tell me? So let's recap here. All right. Right here at when theta is 7 pi over 6 at this critical number, since the second derivative is positive, that means that it is concave up, so we have a minimum. And here, because at theta is equal to 11 pi over 6, the second derivative is negative, that means it's concave down, and we have a maximum. So we can say that f of theta has a relative minimum at theta is equal to 7 pi over 6 because f prime of 7 pi over 6 is equal to 0 and f double prime of 7 pi over 6 is greater than 0. And finally, the last one, f of theta has a relative maximum at theta is equal to 11 pi over 6 because f prime of 11 pi over 6 is equal to 0 and f double prime of 11 pi over 6 is less than 0. And that's your second derivative test. Now these questions here are calculator questions, so I'm just going to pull up my calculator. Okay, so this question reads, the function f prime of x is equal to the cosine of ln of x is the first derivative of a twice differentiable function f of x. On the interval from 0 to 10, find the x values where f of x has a relative maximum and justify your answer. So first we're going to go ahead and graph this function. So that's the cosine of the ln of x. And I'm going to close both parentheses here, enter. I'm going to make sure that I have the standard viewing window, which I do, and now I'm going to graph it. Now, I kind of want to zoom in a little bit more to 0 and 10. So I'm going to zoom in. I'm actually going to change my window here from 0 to 10. And I am going to make my y values a little bit smaller since we saw that it was pretty flat graph. So I'm going to reduce it to, let's say, -3 to 5. I don't know. I just picked random kind of numbers. Okay. Now here on the graph, you can see that we have two critical numbers. And these are critical numbers simply because, remember, we're graphing here the first derivative. So we're looking at the x-intercepts, which is when the derivative is equal to 0. So those are our critical numbers. And you can see that we have two. We have one here and one here. So I want to find those. So I'm going to go to second calc, go to 0, and let's get the first one here all the way on the left. Oops, so I'm going to go to the left bound, so right here, and then the right bound, and then sure, guess. Okay, so we get x is equal to 0.2078. So I'm going to write that down. Oops, 0.2078. And then now I'm going to find my other x-intercept. So now I'm going to go to the left of that one. And I get 4.8104. Now I'm just going to kind of draw a quick sketch here of the graph so we don't have to keep looking at it from there. But, no, wait, let me look at it one more time. Okay, so it looks like this. It comes through here and it goes like that and then back down. So this is one x-intercept here and this is the other. Now when you're creating your number line, because since we're finding maximums or finding when we have a maximum, we want to justify this. Now the number line just again helps us organize the information, but it does not give us any points. So, but this is at least helpful. So this is my first critical number and here's my second. To the left of the 0.2078 is negative. In between the 2.078 and the 4.8104, it's positive. And then after the 4.8104, it goes back down to negative. See how I'm using my graph here? Negative, positive, negative. So where do we have a maximum? That's when the derivative changes from positive to negative. So we would say that f of x has a relative maximum at x is equal to 4.8104 because f prime of x changes from positive to negative. Now on the interval between 0 and 10, we want to find the x values that have a relative minimum. We already did that work up here. So it has a minimum here at the 0.2078. So we would say f of x has a relative minimum at x is equal to 0.2078 because f prime of x changes from negative to positive. Last question for this calculator part. On the interval from 0 to 10, find the x values where f of x has a point of inflection. Now, remember the relationship between the second derivative to the first derivative is the same as the first derivative to the function. So we have a point of inflection when the first derivative has some kind of extrema. So we're going to look here on the graph and we notice that we have a maximum. Now we need to figure out what that maximum is, but luckily for us, there is an option for that in the second calc menu. And you can see that we have option 4 for maximum. So I'm going to click on 4. I'm going to go to the left of the maximum and then to the right and then press enter. And you can see here that we have a maximum at x is equal to 1. So we would say f of x has a point of inflection at x is equal to 1 because f prime of x has a maximum. Now, if the f prime of x has a maximum, that indicates that f double prime of x has changed signs. It changed from positive to negative, and that's why f prime of x has a maximum. And if it changes signs, that's the point of inflection. So that's why we're looking for extrema in order to justify the points of inflection on the function. Okay, let's switch gears now to some non-calculator questions. We have here the derivative g prime of a function g is continuous and has exactly 2 zeros. Selected values of g prime are given in the table below. If the domain of g is the set of all real numbers, then g is decreasing on which of the following intervals? So here we have these values. Now remember that g would be decreasing when g prime of x is less than 0. So we're looking for when g prime of x is negative, which is this section right here. But remember, when we list our intervals of increasing and decreasing, we have to use those critical numbers, which is when the derivative is equal to 0, which is right here. So that would be from -2 to 2. And that would mean that it's option A. Now finally, this one here, we have if h of x is a twice differentiable function such that h of x is less than 0 for all values of x, then at what value of x does the graph of g of x have a relative maximum if g prime of x is equal to 9 minus x squared times h of x? Okay, so first of all, we are told that h of x is less than 0 for all values of x, meaning that h of x is always negative. That means that this here is a negative number, no matter what. So to find our critical numbers, that's what we need, first of all, in order to determine the maximums or minimums, we need to figure out when 9 minus x squared is equal to 0. We didn't have to find the derivative because this is the first derivative. So now we're going to go ahead and solve for x squared, or solve for x. So I'm going to add this x squared over. So x squared is equal to 9. And then square root, we get that x is equal to positive and -3. So these are my critical numbers. So now what I'm going to do is I'm going to put that on my number line here. And I'm going to plug in these values here into g prime, keeping in mind that h of x is always negative. Remember, we don't really care about the value, we just want the sign. And since we know h of x is negative, whatever we get when we plug in here, we would have to multiply it by negative after. So let's say if I plug in -4. If I plug in -4 into this factor, I would have 9 minus 4 squared, which is 16. 9 minus 16 is negative, times another negative, making this interval positive. If I plug in, let's say, 0, then I would have a positive 9 minus 0, so 9, times a negative, which gives me a negative. And if I plug in 4, I would get 9 minus 4 squared, so 9 minus 16 again, which is negative, times a negative, which is positive. So where do we have a maximum is when it changes from positive to negative, which occurs at x is equal to -3 only. Last slide. Here we have the second derivative of the function f is given by f double prime of x is equal to x times x minus a times x minus b squared. The graph of f double prime of x is shown below. For what values of x does the graph of f prime of x have a relative maximum? So we have to keep in mind that the relationship between f prime and f double prime is the same as f to f prime. So f prime will have a relative maximum when f double prime of x changes from positive to negative. So we're going to look here at this graph, and when does it change from positive to negative? And we can see here it occurs at A, and that's it. So at A only. Last question. A table of function values for a twice differentiable function f of x is pictured below. Which of the following statements is or are true if f of x has only one zero on the interval -3 to 3? So we're going to go through each of these options and see which are true. So first it says f prime of x is less than 0 on the interval -3 to 3. So this is the chart here for my f of x values, and this is from -3 to 3. Now, if f prime of x is less than 0, that means that my function would be decreasing. And you can see here that we go from 10 to 8, then from 8 to 2, and then from 2 to -13. It is always decreasing. These numbers are getting smaller. So this is true. F of x has a 0 between 1 and 3. Here is 1 and 3, and it goes from a positive number to a negative number, meaning that it must have crossed the x-axis at some point, which is that it has a 0 because y would equal to 0. And this is also, if you remember, IVT. IVT tells us that if our values on either side, right, if one is positive and one is negative, then there must be 0 right in the middle. So this is also true. And finally here, f double prime of x is greater than 0 on the interval -3 to 3. So if f double prime is greater than 0, that means that f prime of x would be increasing. And I'm using f prime because f double prime of x is greater than 0 says that my function is concave up. And without a graph, it's kind of hard to tell whether my function is concave up or not. But if I could find the rate of the change here between these y values, then that's going to tell me whether my f prime is increasing or decreasing. So if I just subtract, 10 minus 8 is -2. 8 minus 2 is -6. I'm sorry, I have to go backwards. 8 minus 10, because these are the successive positive values. 8 minus 10 is -2. 2 minus 8 is -6. And -13 minus 2 is -15. And if we look at these values, it is also decreasing. So if this is also decreasing, then that means that f prime would also decrease. So since it's not increasing, this is not true. So the only things that are true are statements 1 and 2. I know this was a lengthy lesson, but thanks for sticking to it. And that's all the connections between our functions and their derivatives.